All right, good.
Okay, welcome everyone. We're very happy to see so many attendees. I see 28. So this is our very first online tutorial. This monthly series started last year. It's been organized together with PAC, Postdoc Association of Colorado at Boulder. And it's always been in person. This is the first time we've done it virtually, and we're very glad to see so many people. Probably this is also going to be the last of this semester. I mean, the last one was probably going to be in May, but as far as the semester is going, this is going to be probably the last. But we always love feedback. So please, if you have any feedback about today's session or other sessions, if you attended in the past, please let us know. I'm Valeria, by the way, the organizer of this series, and Manuchehr from CSU in Fort Collins is the tutorial presenter of today. So thanks so much, Manuchehr. I'll turn it to you.
Thanks. All right, I'll share my screen. I promise this isn't going to be all slides, but I'll start with a few slides and just kind of introduce myself a little bit and give an idea of who I am and where I'm coming from and what all this is going to be. So first of all, who am I? I like to do this in a lot of talks, just to show a bunch of images from throughout my career as an applied mathematician. So in undergrad, just to give you an idea, right? You're going to see this again and again. I'm going to probably say it a lot of times. I'm not really a data scientist. I'm an applied mathematician primarily, so I've done a lot with like numerical analysis, image segmentation. That's these horses in the upper left you might recognize if you've done similar work. For my PhD, I did a lot of stuff in partial differential equations, a little bit on the analysis side, as well as a lot of numerical simulation. In my postdoc, I've done a degree of analysis of algorithms relating to shape and data. So that's the stuff on the top, having to do with measuring fractal dimension, actually, given point clouds sampled from approximations to the Sierpinski triangle. You don't have to understand these words. I'm just giving you an idea. And then what really pays the bills for my postdoc is a lot of analysis on human challenge studies relating to influenza, actually. So to some degree, very relevant to what's happening nowadays, but the grant actually ended about half a year ago or a little bit more now. So to some degree, we're trying to just push out the research that we'd already done previously. So before you ask if I have a hot take or something deep to say about the current crisis, I mean, maybe a little bit, but not really much more than that. Yeah, so that research involves both working with gene expression data and time series analysis having to do with wearables. Anyway, those are some pictures. I am an applied mathematician, so I think when I'm giving talks and talking about this, I have to sort of give a pitch of what mathematicians have to do with data science, right? Why am I even giving this tutorial to begin with? I'm going to say this and then not actually do any of it in my own tutorial, but our pitch is basically that we have something to say about understanding shape and data. So on the left, what this is basically visualizing is a low-dimensional representation of gene expression data. We measure thousands of genes taken from someone's blood, and each gene counts as its own dimension in the data. And what you can do with a few tricks and some mathematical tools is identify what's approximately a loop here. So these are people that are intentionally infected with influenza, and this color bar represents the number of hours after they've been infected. So in some sense, the black is 0, meaning pre-infection, healthy, and 24, 48, 72 represent the number of days since that's happened. And if you really squint your eyes, you can kind of see a loop happening here. Okay, that's a very rough argument. This loop isn't really very clearly distinguished, but if you look at like pockets of high density points, every point representing one of these blood samples, you can kind of pick out a loop from healthy to sick, and then all the way to day 5 is these yellows. You're kind of returning back to this healthy state over here, principal component space. And you can do similar things with time series analysis. So if you put on a watch on someone and measure something like temperature, well, actually this is from a mouse, so disregard the fact that I said human, right? This is from a mouse. and you apply some approaches to embedding this data in higher dimensions. So you're just only measuring temperature, but you're taking multiple temperature measurements from different times. You can actually pick out a loop in that regard as well. And this loop might represent the healthy state in this case, and then deviations from that can represent the fact that someone's getting sick. Okay, so this is something that, while maybe statistics or computer science can say they do similar things, I think mathematicians have the main role here. Like, we are the masters of this domain more than the others. We just pay lip service to it. Okay, as far as this tutorial, what it is not going to be, I think it's worth mentioning. It's not a talk on any of this research aside from the preview that I just gave you. It's not a talk from someone coming from as an expert in data science, right? Because I did PDEs for my PhD. I've only been doing data science for 2-ish years. I haven't done any real industry projects aside from maybe a workshop during the summer that's really oriented towards math people trying to transition into data science. So, but I haven't done any. I've been paid. Let's put it that way. I've been paid to do data science. I haven't had any formal training, right? So I'm not going to necessarily teach you the best practices. When you look online and see a tutorial, you might see some things that are different from what I'm going to do. For this last part, I don't know if you read the flyer, right? But this last part is going to have to do with analyzing text from papers. I'll just say this in advance. I haven't really done much work with it other than loading it, but that's kind of what I pitched anyway, so I'm not going to disappoint you. But in particular, I'm not doing a lot of natural language processing, so you're not going to see a lot of complex models for analyzing sentences or doing embeddings with them. No word to vec or doc to vec or whatever to vec it is nowadays. Okay. What I am going to do is give you a tutorial. As I mentioned, I've been dabbling in data science for the past 3-ish years for my postdoc. And it's going to be a lot of basically follow along with me as I code. And I'll try to explain my thinking, but you really should stop and ask me at any time if you have a question about anything. Okay, because why, right? You should ask yourselves, live intentionally in general, right? But go to talks intentionally. You should ask, why are you here? And maybe it's one of these first 2 points, right? Maybe you're a friend of me. I think there's a few of those in the audience, and you're a nice person. It maybe breaks up your day, right? But in reality, probably most of you are here hoping you learn to pick up something, learn something. Okay, then you ask, given everything I've just told you, why are you doing this rather than doing a Coursera course if you really want to know data science? Okay, and the answer is probably that it's easier to learn something if you're interacting with someone. So this is really just my pitch to stop me at any time. Okay, ask me questions about anything, big or small, about anything. I'll get to coding and pictures in a second, okay? But this is just a recapitulation of what I've shown in my poster. I'm going to be demonstrating different aspects of data science and how the types of problems we answer and how we think about things by working with 3 data sets. The first 2 are from a nice online repository of relatively clean data sets. The first one is very famous. It's called the Harvest Data Set, where you're trying to distinguish different types of flowers. The second one is from that same repository, but maybe less famous, having to do with a collection of wines. There's some thousands of numbers of wines where they measure different properties of the wine, and then the goal might be to judge what kind of quality wine. Is it like a bottom shelf $5 bottle of wine, or is it $50 or $100 bottle of wine as judged by somebody, right? So there's a quality score attached to every single wine, and then try to distinguish things about that. Or even just pick up the fact that it's a red wine or a white wine, right? We'll be doing some of that. And then this last part, which is going to be, either time permitting or how much you all want to bear with me while I basically do this live, right? I'm going to be working a little bit with a data set that's very recent, related to preprints of papers on bioRxiv and medRxiv related to COVID, or in more general relating to coronaviruses. Okay, so there's this open data challenge where they put up thousands of papers and relatively easy, right? I say this in quotes generously, relatively easy to load and analyze, and try to discover something of it, because as it is, right, it's a huge mess of basically everyone trying to contribute something. It's hard to really learn anything at the moment. That's my impression anyway. Okay, so if you're going to be a data scientist, right, there's a collection of ingredients that you really need to build up over time that you need to succeed. In my experience, everyone I've interacted with, the main language is Python when it really comes down to it. I think some people are experienced with R, right? I think there's definitely a subset of people who still work in R, but maybe it's bias of who I happen to interact with, being a mathematician, but really the language is Python. The more you code, obviously everyone understands that the main algorithms translate across languages, and it's a matter of learning syntax, but learning the syntax is a small barrier of its own, and how people code in languages. In particular, many people work with Jupyter notebooks, so that's what I'm going to be doing during this presentation. I'll actually say in advance I have a mild dislike for Jupyter notebooks, but not enough to stop me from using them. And some more, I don't know how to call it. It's not really a soft skill, right? But it's not like something you can get really a certificate in. But things like working in a command line, understanding conventions of like how do you access data, how do you refer to data, how do you find the data that you want, how do you load it. This is whether or not you're working in Linux. So I'm actually on a Windows laptop right now, but many of the same approaches are common across operating systems. Especially once you're working in Python, it doesn't matter quite as much which operating system you're using, but there's some tools you need to understand. Okay, and then I've listed a collection of Python packages. In my flyer, I listed the first 4 of these as mandatory. So that's what I'm going to be using for coding and analyzing this data. Another skill is just simply being adept at learning to load and study data. So something I don't have on hand, but maybe I can share in my GitHub repository is the history of commands I had the first time I was loading this collection of COVID papers. So it's very funny to see the amount of wrong commands I have and errors that I have. Just the entries that I'm typing in, I get an error and I say, oh crap, to myself. And then I change it by 1 letter and get another error and say, oh crap, to myself, and then get another error. Right? But nevertheless, right, over time, say, oh crap to yourself fewer times and get more adept. Yeah, and then this last one I'll point out is that, yes, I still use Stack Overflow and package documentations, but it is really a skill to evaluate, is this advice useful or not? Because I have myself and looking at other people's code always, or sorry, not always, many times experienced that I could easily pick out, oh, this is a solution they found online. This is overly convoluted with what they're really trying to do. Is there an easier way? And oftentimes there is. Okay, so being able to judge all these things is really something you need to get practiced at if you're going to be a data scientist. Okay, so let's jump into it a little bit. 2 more slides, I think, and then I'm going to get into the Jupyter notebook, and then you can code along with me and stop and ask questions at any time. Be sure to unmute yourself though first, because I'm not watching chat right now. Okay, so this iris data set, as I alluded to, has to do with picking out different types of flowers. In particular, there are subspecies of irises. Okay, I think the 3 species, well, you'll see them on the next slide. But the point is they measure basically 4 different things about these flowers. And the goal is to say, given a new flower, let's pretend we already know it's an iris, and we just have the 4 measurements. Can I pick out what type of flower it is? Okay, so general goals we're going to do, what we're going to try to demonstrate with working with this data is understanding a little bit about your data, right? Like that you need to not just work with numbers, right? But you have to understand where it's coming from as well, to understand the caveats of what you're doing, or whether what you're doing makes sense or not. And this is simply an iterative process, right? Even though I've, on my GitHub, which I'll highlight in a second, I've uploaded a script which loads this data nicely. In practice, you're not going to get it right the first time. This is an iterative process. You just have to keep pushing through. And then, yeah, we're going to introduce a few basic ideas of classification and regression on data. Okay, so this is my one pretty slide. thanks to PowerPoint, one of its suggested formats turned out nicely. I put up this slide, well, the information's on the left, right? So these are the 4 measurements that we're working with. They take one of these types of flowers, as listed here. They measure sepal length and width, petal length and width, and then the goal is to classify, okay? And so if you stare at images of these flowers, you can say, well, wait a minute. I mean, that's all well and good that you measure those 4 things, but if you're really trying to distinguish these types of flowers, by eye, you can easily pick out a lot of different properties that really distinguish these 3. Okay, I'll let you think for a second. I think the first one for me is color, right? I mean, they're all kind of purplish, but definitely the setosa and versicolor are deeper shades of purple than the virginica. I don't know if I'm pronouncing these right. And then if you stare at these yellow okay, obviously I'm not a botanist either, right? But if you stare at the yellow portions of these flowers between versicolor and setosa, it seems like there's very different patterning that's happening. So yeah, so to some degree, right, if your only goal was to classify different types of flowers, these 4 things are probably not the best idea, right? But it's an interesting question in its own right. If you can only measure these various lengths, right, and disregard all color information and patterning, what can you do? Okay, so keep that in mind, right? The limitations of what you're doing, and if you were allowed to measure more things, what would be useful? Okay, so let's jump into it. Coding part of this, most exciting part. So what I'm going to do is, and I encourage you to do the same if you're interested, open a new Jupyter notebook. Okay, I already have this loaded, right? But make sure that you're in the folder that contains that's set up for this problem. Okay, so what do I mean? If you haven't prepared this in advance, this is something that you can do now. I believe the flyer has a link to my GitHub because I mentioned that the data is available there. This is me. Links to the data are available there. I mentioned a helper file, which is also in this main repository. If you're not familiar with how to work with GitHub, you're not going to do very well in getting off the ground. Well, in particular, you can't use this utilities file. But in short, what you can do is say, if you visit this website, click clone or download, and download in desktop. Sorry, download in zip, unzip, navigate to the folder, and open it. Okay. Does anyone have any questions about this, by the way? I mean, I don't want to derail things entirely, but if there's anything quick, I'm happy to answer as far as downloading the data, accessing it. In particular, this iris, if you visit this link, this is the main repository I was mentioning. And if you want the data, you go to this data folder here. And then it's this file called bezdeciris.data. If you stare at this previous page, they explain why it's that file. There were some errors apparently in some of the measurements to begin with. So I believe the bezdec one is the one that's corrected. Okay, so if you've done things in the way that I'm expecting that I'm going to be working off of, what you'll have is some folder that looks roughly like this. If you clone directly from GitHub, it'll look like DS Tutorial 2020. There'll be a collection of files, maybe not these IPy notebooks, but you'll have a file called readme.md, have a file called utils.py, and you'll have a folder called datasets. In this folder, let's see if I can zoom in a little bit. This will be empty except for a file that says put data here. You should just follow the instructions and put your data there. Okay, so in particular, this bezdec iris data, I've put this file here. Cool. Okay, so the first thing that I do when I have a new data set is ask what type of data is it? Okay, and you don't necessarily even need Python to do that. I'm working in Windows, right? But regardless of your operating system, you can just try to open the file using a text editor to begin with and just see what happens. Okay. In this case, we lucked out, okay, meaning that I said open in Notepad++. That's my text editor of choice for the moment. And what I got out of this was a collection of rows of things, right? You'll notice there's numbers 5.1, comma, 3.5, comma, 1.4, comma, 0.2, comma, and then this looks like the type of flower, okay? And so if we compare it to what I've already told you already, meaning there's these 4 measurements, well, I can pretty confidently say that I'm going to associate that with each row here. So it seems every row here is a flower. These are the 4 lengths or widths that I'm measuring in centimeters, and then the corresponding flower. Okay, and if I scroll down, I see that, yes, there's some versicolors in there, and then further down, there's virginicas. Okay, cool. So this is a pretty common format that's called comma separated values, or CSV for short. The fact that this file ended in .data doesn't really mean anything other than, you know, the person who saved it and uploaded chose to use that naming scheme, okay? But it's not a specific file format that you load using something, okay? You'll see this often, right? People will use any kinds of suffix or no suffix at all when in reality their data is nicely organized like this, right? Numbers or text that's separated by some kind of what's called a delimiter. In this case, it's a comma. Okay, so all of that in mind, what am I going to do? I'm going to pull up my Jupyter notebook for now. I want the nice one. Okay, so here's my blank Jupyter notebook. I'm in Windows, so when I type ls, it gives me the Windows formatted version, right? But you should just do this to make sure that you're in the working folder that you're expecting to be in. In this case, the data science tutorial folder. Okay, I am good. I don't need this anymore. Okay, I'm going to import all the packages that I really like. Zoom in fact. Okay, there's PyPlot. That's my visualization tool. NumPy is my catch-all tool for processing numbers and working with lists and arrays of numbers. Pandas, maybe. And then I'm going to, in fact, use my utility file. Okay, so this file in particular is not a default Python package. It's not something you can download online. It's this specific file that I wrote for the purpose of this tutorial. Okay. And inside of it, I have nice scripts for loading this data, which I'll highlight a little bit more on the Wine data set. But for the moment, I'm just going to streamline that part for you. Okay, so follow along with me. I'm just going to run this command. Okay, so this is my convenient loading script for loading this iris data in particular. It ran and it didn't print anything, so let's take a look at what I've done exactly. If I type data in and run the cell, I'll see that this looks like the first 4 columns of this file that I opened. Okay, and then what I'm calling labels is an array of strings, words, right? So these are the corresponding flowers. Okay? And we use the word labels in general as a catch-all in classification problems. Okay, meaning you're labeled either a iris setosa, or you're labeled a versicolor, or you're labeled a virginica. Okay, so
I have a quick question, Nuj.
Yeah, of course.
So usually this iris data set, it comes pre-packaged with other packages, right? Like sklearn and all.
Yeah.
Is there any advantage of doing it manually like this?
So if your data is not extremely clean, then you do have to do things fairly manually. I think you're talking about like sklearn, their stored version of iris.
Right.
Yeah. If you're working with that in particular, probably not. but chances are you're going to work with a data set that's not available in their set of default packages. It's going to be the same numbers and the same labels probably, and probably in the same order even. Yeah.
Okay, thanks.
Yeah. Yeah. So if, for those that are interested, if you were to look at the utils.py file, this module that I wrote, I actually didn't even use what's considered kind of like the default tool for loading CSV files, right? I did things manually in yet one more step, but I'll get to that later. Okay, so what does this data look like? This is where you need a little bit of familiarity with pyplot and matplotlib. Okay, you'll notice that there's 4 choices of variables, right? I can't actually visualize things in 4 dimensions, and I don't know if you all can either. Okay, so just by choice to begin with, let's start by doing something arbitrary, okay? So what I'm gonna try to do is just make a scatter plot of my data, picking the first, that is to say the 0th thing. That's my, where is this? That's my sepal length. And then I'm gonna take my sepal width, that's the first coordinate, just scatter plot and see what I get. Okay, and so that is what it is. There's a few things missing here though, right? In particular, all these dots look the same, so I can't really pick out what is each subspecies, right? Where do these lie? Are these arbitrarily ordered? Is everything nicely separated? Or are they colored based on which point they happen to be? Okay, so the first way to improve this plot, right, when I'm still exploring the data, is to, per flower basically, plot it with a different color. Okay, so I'm gonna do a trick that I will use over and over again, and make what a mathematician would call an equivalence class. Okay, what I'm gonna do is basically say, given my list of labels, which are the different flower types, take all of this Setosa data at the same time and scatter it, and then only take the versicolor data all together and scatter it, and then take all the Virginica data at the same time and scatter it. Okay, so I'm going to build what's called an equivalence class. I'll use a dictionary to do this, where what I'm typing out is basically what I just described. I'm finding where I have a specific type of flower. There's some small details in the way I'm doing this. Okay. But this is the basic format. Okay, so there's a little bit of Python magic happening here, but this is more or less a for loop saying for each type of flower and what are the unique list of labels, meaning there should only be 3 things here, the 3 types of flowers. Find where, meaning the 0th entry, the first entry, I think this is up to entry 45 in this case, right? But I'm saying find where in my list of labels I happen to be one type of flower. Okay, so let's just see what this gives. If I were to type EC by itself, this is indeed what happens. Okay, so this is a Python dictionary where I say, if I take an input that looks like Iris Setosa, it's going to give me a list of what a computer scientist would call pointers, right? Locations in my data where this is the flower in advance, okay? Why does this help me? Because I can basically do this 2-liner. Like so. Okay, and there you go. Okay, so this is loop is again using some little bit of Python magic where I'm saying take each flower type and the corresponding indices. Okay, that's what this for KV and EC.items does. And I'm saying scatter only that subset of the data. And if I want to go one step further, and like I don't know what oranges and green are, these are just the default set of colors that cycle through in Matplotlib. I will attach a label to each, and then after the fact, make a legend. Okay, cool. So that's awesome. This is maybe the one place where Jupyter Notebooks do shine. I mentioned that choosing the first two measurements as my coordinates is arbitrary, admittedly. Okay, so you can play around with this. You can say, well, what if I take coordinates 0 and 2, or 1 and 2? Okay, for every single choice here, you're going to get a different type of scatter plot, because I'm just picking 2 of the 4, and there's something like 6 to choose from. Okay, and each one will give a different kind of picture of, only looking at these 2 measurements, how well does this data separate into different classes? Okay. And you'll notice in particular, I just bounced through a few, right? But if I look at numbers 2 and 3, and again, Python language, add 1, this is saying measurements 3 and 4 really. This seems to do pretty well, actually, right? Visually, right? All the setosas are well separated over here. And then the versicolor and virginicas, it seems like there's some overlap in these 2 distributions, right? But they do separate relatively well. Okay, so it seems promising if we were to even just stare at these 2 variables and disregard the other 2, that I could come up with some rule, right, for trying to distinguish these things. Does anyone have any questions so far? While I drink water. Okay, so I haven't done anything magical yet. Where does the data science come in? I'm just writing a comment to myself here. Okay, so I didn't import sklearn here. Okay, the data science portion where I'm going to do classification is going to come in now. In particular, I want to use a specific type of model, okay, which is, say, a linear model. Okay, so one of the most basic approaches to classification that you can do when you're confronted with a data set like this is to come up with a rule that says, find me the equation of a line in these 2 variables, right? So variable 1 is, help me, petal length, right? Variable 1 is petal length, variable 2 is petal width, right? So I could say, find something like 3 times petal width plus 4 times petal length minus 5. Okay, if I were to take that and make a line out of it and graph it, what I would hope is if I choose these coefficients, right, not 3, 4, 5, but maybe it's 0.2, 0.1, 0.6, I could maybe find a line here that perhaps separates out the blue from the orange. Okay, and this subset of the scikit-learn package called linear model is filled with the various approaches towards doing this. In particular, I think what I want to do is, which one of these do I want? Which one do I want? In fact, I take that back a little bit. We'll come back to this. Okay, linear models are great. The linear model that I want is actually called a support vector machine. Okay, so what I want is something that's called a linear SVC. Okay, so SVC stands for support vector classifier. Okay, in more general terms, you'll hear the word support vector machine thrown around. It's fancy words for really what I just described. Find a line, or in higher dimensions, the word is hyperplane, right? Find the equation of a hyperplane that does well in separating out one type of data from another, okay? Okay, so the way that sklearn works, right, the methodology that you have to learn is that you make an instantiation of this class. Okay, so this is an object-oriented programming thing. Okay, so I instantiate it, meaning this SVC is a thing which has functions inside of it and might hold information about your data and your labels towards building this model. once I feed it to it. Okay, so you just instantiate it, is the word, by opening and closing parentheses. And then when I want to tell it to find the equation of the line with some underlying algorithm, right, for finding these coefficients. When you're working with scikit-learn, the convention is always the same. Okay, you start by doing fit, right? This svc.fit means apply this function and find coefficients given the list of data organized in rows, which we have, and the list of corresponding labels for each row. Okay, the labels here are one of the 3 flowers. Okay, so this output looks exactly the same, because that's just how these work. But if you want to see if it did anything, right, whether it actually fit the data or not, the first thing that you can do is look at one of the variables that it stores. Okay, so if I type svc.coef, okay, there's some complications under the hood, but the point is that this is a list of numbers. These numbers aren't random. Okay, so if just to demonstrate, if I were to rerun this cell and don't bother fitting, and then type svc.coef, you're going to get an error, I guess, because it hasn't bothered to fit anything yet. Okay, so this coef is really an array that's storing the coefficients of your linear model, which helps to separate one type of data from another. Okay, so, and as you know from algebra perhaps, every single line has an intercept, and so indeed there's also an intercept array. Okay, storing, in this case, 3. Okay, so those 2 things are now calculated. Maybe I'll poll the audience briefly. Does anyone have a sense of why this looks the way it does? So first of all, what are the shapes here? Okay, so this is an array that is 3 long and 4 wide. Does anyone have a guess as to what these things are? Anyone brave enough?
Normal vector to a hyperplane?
Yes, but which part of that is the normal vector? Okay, yeah. So my hint is that the data has 4 dimensions to it.
Right.
So yeah, that's...
Yeah, each row is a vector.
Yeah, exactly. Yeah, so yeah, these are the normal coefficients of the hyperplanes, or stated another way, these are the coefficients multiplying each variable when you build your linear model. Okay, but why are there 3? Okay, so I kind of brushed over this fact, but if you start this data again, well, there's 3 types of flowers, right? Okay, so if you have 1 line, how does that work exactly, right? So this kind of gets this idea of binary classification, where you only have to separate 2 types of things, versus multi-class, which in our case there's 3 classes, where you have to separate different types of things. Okay, and you can't just use 1 line to separate out 3 different types of things, is what it boils down to, right? If my rule is, am I on one side of the line or another, just 1 line isn't going to cut it if I'm trying to separate 3 things. So in reality, I have to say, find a line that separates blue from orange, find a line that separates blue from green, find a line that separates orange from green. And that's why I have 3 things here. Okay. Okay, so I really want to show you a proof of principle that this does actually, in fact, work. It's just a little bit of jumping through some hoops. Well, no, I take that back. There's a way to do this. Okay, so if you really want to see that this is kind of doing what you expect it to do, okay, another tool that's built into this support vector classifier is something that's called the decision function. Okay. Now, under the hood, many classification tools, which give you a binary or a categorical answer, meaning just 1 of 3 categories, under the hood are attaching a numerical value and doing threshold, right? So that's to say that maybe blue is assigned the value -1 and orange is assigned the value +1 and the green is ignored, right? So in reality, after this model is fit, maybe these blue ones that are closest to orange have a value of -0.5. The ones further away have a value of -1.5. And then the orange values are all positive, so that when you threshold and say, am I bigger than or less than 0? This is really what gives you a classification, okay? And so to give you an idea of what this looks like, let's see what happens here. Things are a little bit different at the moment because I'm working with 3 classes and things are a little more convoluted, okay? But I believe what I'm going to want to do is work with this last set of data, this last column, and apply my same scatter plot. Okay, so here's what I'm going to do. This is not actually the approach that I did before when I was preparing for this, so pray for me a little bit. Okay, but I am pretty confident it'll work out. Let's just call it vals. Okay, what I'm going to do is, rather than in advance making a scatter plot of each thing by label, what I'm going to do is color based on the value here. Okay, the PyPlot package has built-in tools to control the range of the color map, just like in MATLAB or any other plotting software. Oops, let's run that, rerun. So that when I do this, what the? Oh. So that when I do this with all of the data, you'll notice that, okay, if I'm coloring based on the decision function, these are real valued things, so there's a kind of a smooth gradient happening here. Okay, if I just attach a color bar really quickly, you'll notice that everything in dark blue is very negative, right? That belongs to this class. And then everything that's in this greenish region and above, meaning the points up here, are all in the other class, okay? So if I were to threshold, it would mean drawing this, yeah, indeed, the hyperplane where this decision function is 0, which is this middle greenish area in the middle here, okay? And then really some of these flowers in the middle would be called setosas. So some of the versicolors would be called setosas, some of the versicolors would be called virginica in a binary classification. And like with all Jupyter notebooks, you can play around with this and see what happens if you plug in different numbers. All right, so I think 0 is the other one I'll highlight. I believe, yeah, so this one is distinguishing setosas versus versicolors, right? Which is why, again, you stare at this value at 0 is this middle green color. And you'll notice these are deeper shades of green, so it probably is classifying this group versus that group for this first model. Cool. Any questions with that? The last thing I'll point out is that okay, the next common step with classification is really asking how do you do in predicting. So I'm going to be doing what's called predicting on training data, meaning that when I did fit, right, I said, here's my entire data set. Oh, I think I got a chat question. So yeah, so I can re-show the commands from the top. So to briefly recap before I conclude, right, what I'm going to do is say import all the tools that I'm going to use, with the exception of maybe sklearn. In particular, I only used SVM. Okay. With this GitHub tutorial, right, with this data science tutorial, I uploaded a script on GitHub called utils, which loads this data set nicely, at least for how I'm doing it here. Okay, and I'm exploring this idea of scattering the plot, scattering the data and choices of coordinates to kind of see what it looks like. You have to do a little bit to make it look pretty, meaning if I want to color based on the type of flower, I have to, in advance, subset the data. Okay, so maybe this is the most complex command that I'm doing, and I can probably break this up a little bit to help visibility a little bit. Right, so what this is building is a Python dictionary where you say, take the type of flower, find where in my data I have that type of flower. You need this 0, but it's just a detail. Okay, and then I'm saying loop over the unique set of 3 flowers that I have. Okay, I'll be doing this again and again, so you will see that again. And then I did some data exploration, okay, where I said loop over the types of items that I have, right, meaning flowers and their locations, and scatter each piece separately. So I did this pyplot scatter and say plug in my x coordinates, what I'm calling x coordinates, plug in y coordinates, and then attach a label to those so that I can later make legends. Okay. And these choices of 2 and 3 are arbitrary. You can feel free to pick different dimensions to look at. Okay, so the data science portion came in, right, when we were addressing this point of classification and regression and using what's called a support vector machine. Okay, so you actually don't need this again if you import your SVM at the top using this command. Okay. The typical classification methodology involves fitting your data using sklearn. So you say instantiate the object, meaning the tool that will build your support vector machine and tell you the coefficients. Okay. First fit it using your data and then the corresponding labels. And then you don't really need to print these, but if you want an idea of whether it's worked or not, you should print. And then again, this is evaluating what I've got out of this model. And then what I was really demonstrating here was what this underlying linear model does. So I'm saying use something called the decision function to evaluate for every single point, does it belong in one class or another as decided by are you bigger than or less than 0? Okay. So the last aspect of this maybe that I'll address with the iris data set is the prediction step. Okay. So if I predict and I feed it in the same data, this package has built-in tools to just give you back the same things that you feed it in. So I mentioned this whole idea of assigning -1 and 1 to my data points, but you don't have to think about that at all. You can just stick with the plain text names of your flowers. Okay. And so I gave it all the original data to predict as well. You're probably going to expect that most of it succeeds. Okay, it's hard to tell by eye. So what I'm going to do is do a small miniature version of evaluating my prediction. Okay, so what I'm going to ask is, where is my predicted not equal to labels? Well, first of all, if I do not equal to, I'm asking, where does this not happen? Okay, so if I were to take one step back, actually, I'll do these 3 things in sequence. First, just to give you an idea, I'm going to look at the first 5 predicted and true values for the labels. Okay. My thinking is I'm just going to compare where these don't match up and where they, okay, to get a sense of how well I've done. So the first 5 match up. That sounds great. I think this is this group down here, so maybe it's not a surprise that I did really well in predicting these. Okay. So if I do, let me move this to a new cell. If I ask, where's predicted double equal to labels, that's doing a piece by piece comparison. Okay. And so if they are the same, it tells me that yes, they are the same. If they don't match up, it gives me a false. And so you will see there's a few cases where it didn't predict correctly. Right? So there's maybe 1, 2, 3, 4, 5, 6. If you do not want to do this by eye, okay, you can do something like this. Okay, you can basically add up all the places where this is true. Okay, so it seems like I got 145 correct of 150. Okay. And more precisely, you know, if you want a number, you can indeed do something like sum. Right, this is just a simple accuracy, asking how many did I get correct. I'm not looking at false positives or false negatives or anything like that. So if this were a student in my class, and this is really an interpretation of what I've just done. You tell a student in advance what's on the exam, you give them the exact list of problems, right? And then you tell them, here's my list of problems, take the exam. They've just gotten a 96.6%, okay? And you might say as a teacher, well, that's kind of a flawed process, isn't it? Because you're just telling the problems and the solutions in advance. Yes, that's the case. That's the case. So in this next part, I'm going to allude to a slightly more complex workflow.
Can I ask 2 quick questions?
Yeah, of course.
So one is in running the SVC function, I had to actually increase the max iter because I got an error. Is there any recommendation for how high you can go with that?
I wouldn't give you a hard number. The short answer is as long as it runs quickly if you're working on your laptop. That's a little surprising though with this data set.
Yeah, it ran really quickly and the numbers that I'm getting are very similar to yours. They differ in like the 5th decimal place. So.
Oh, you're staring at these ones, you mean?
Yeah.
Yeah, sure. That's interesting.
Not sure why that happened, but it worked if I increased the max iter.
Yeah.
My second question was, how does one interpret the scale on these plots again? You said something about greater than 0 or less than 0. Can you just explain that again?
Yeah. So under the hood, what's going on? So if I were to focus my attention to just blue and orange, okay, and ignore the green completely, right? What you're doing is to find these equations of these lines, you're attaching the value of -1 to all these blues and the value of +1 to all the oranges, okay? And really what you're asking this SVC, the support vector classifier, to do is find me a line, right? Really, it's a linear function, right? That gets as close to a -1 as possible for all these blue data points, and as close as possible to a +1 for all the orange. It's not going to be perfect, right? But even if we get the sign correct, we're happy with that. Okay. So the decision that this classifier is making is saying, hand me a new data point, meaning petal length and petal width are these 2 coordinates in this plot, right? So if you give me the petal length and petal width as values in centimeters, and plug those into this linear function, I'm just asking, is this positive or is it negative? Okay. The part that's a little bit of a chore to visualize is actually plotting this line to begin with. Although I take it back a little bit, so I can just, let me do this. I think I kind of want to do this. I'm gonna revisit this because I think it's really good to have the picture. Doing things a little bit manually. If I know that I'm looking at these 2 numbers in advance, okay, this is really what's happening. I'm saying take something like 1.38, I don't care about all these decimals, x plus 1.86y, and then what's my intercept? I want to look at the third one here, minus 1.7. Oh, okay. The decision function basically says set this equal to 0 and solve for y. Okay, so doing some quick maths. I'm gonna try to solve for y and give you a plot actually because I'm kind of curious myself. 1.70 minus 1.38x all over. There's more sophisticated ways to do this, but just for the sake of argument, I don't want to deal with mesh grids and contour plots and all this junk for the moment. Okay, so my argument is if I were to plug this equation of a line and plot it in here, I should get a line which separates out my blue and, well, maybe we'll find out. I don't want to say it too confidently right now. So this is the extra credit part. Okay. Just do it this way. So I'm pretty sloppy with parentheses. I think that's the same function. Drum roll, you can all do drum rolls in your head. Is this gonna work out? Oh no, oh no. What happened? Well, okay, so this is kind of the picture. If I wasn't doing this live and doing this properly, right? What you would see if there's this black line would separate out either the blue and the orange, or the blue and the green, or the orange and the green. The chances are I just mix the order of some of my variables. But I mean, that's the idea. Does that help at all? Or?
Sure. Sorry, I'm still absorbing this.
Okay, yeah. I know it's kind of a lot, right? I would say if you understand this line represents a rule of basically, are you on one side or the other? That's how you're distinguishing two types of flowers.
So does it mean a value when we plotted the scatter plots and we had ranges that were closer to 0? Is that not a good separation then? Is it?
Yeah, so it depends on, okay, since there are 3 classes, you have to take it a little bit with a grain of salt, but yeah, correct. If you had something close to 0, these would be things that are hard to distinguish from one another, right? So if I revisit this cell, let me see which one of these is the one I'm interested in. 2 maybe. So in fact, coming back to this again, I think it's probably this one is trying to separate out the orange and the green, right? So in this last one, my dividing line is in the greens. So yeah, you can see there's a lot of points that are close to 0 in the middle here, right? Definitely these ones are 1 or 2 or greater, so no problem classifying these. No problem classifying these ones away from here, but there is a gray area in the middle. Yeah.
Okay, thank you.
Yeah.
Does it literally mean distance in the normal direction from the plane? Is that the value?
Well, almost. It was more or less yes. Like I would say up to a constant, whether it's additive or multiplicative. This is the decision function value. I don't want to say it's actually the normal direction distance, but yeah, the underlying tool relies on this idea.
Okay.
Yeah. Cool. Yeah, there's a lot of different things you can do with this data set. I'm curious if I have anything else in my own analysis that I didn't highlight here. Anything fancy I did? Yeah, so for instance, here I was a little more careful and I could actually plot out, I focused my attention to 2 of the flower types, and then I actually did plot the contours of my decision function. So where that function is 0 is where I'm making my decision. But you can ask, where is it 1? This is solidly in this blue class. And then the negative ones are solidly in the orange class. So this is the proper picture if you do things carefully. I think that's about it. Something else I could highlight, but I'll pass on for now, is that there's many more high-level tools to speed up your early analysis. One in particular is called Seaborn. This is yet another visualization package kind of built on top of Matplotlib, which can do fancy things. So there's this part where I was just saying, oh, let's look at 0 and 1, 0 and 2, 0 and 3, right? It has a nice function to basically do all combinations for you. So this can be really useful to explore data. If you have a small number of variables, okay? If you have 4, it's nice, but if you have 100 or even 10 or 11, as you'll see in a minute.
Could you show that cell again? I just was copying the Seaborn.
Oh, this one? Yeah, sure.
Yeah, Seaborn.pairplot.
Yeah. And it actually speeds up some of this equivalence class stuff as well. So it can be very convenient, really, right? It takes care of all this per flower labeling. Yeah. Okay. So I'll move on. we have about 30 minutes left. Okay, so the next data set that I'm working with is called Swine Data Set. The goal is, like I alluded to, distinguish something about wines given chemical measurements. Okay, I wanted to highlight in particular that you want to do it with only a few measurements, because I think this is an aspect of data science that comes up again, especially if you're working for, like in the private sector, where someone has to make a decision. They say something like, I want to predict, I don't know, profits, right? It's always profits or something like that. Again, remember my caveats, I've never worked in the private sector, right? But they want to make a decision on something. If you tell them, well, I made a linear model, and even though you gave me like 300 things to choose from, I was able to predict, but you have to track all 300 things, various aspects of industry. And to them, that's not really useful because, well, I mean, depending on the context, that's not something they can make a decision on. Okay, so oftentimes people want a short list, like, well, what's most important, right? What should I really pay attention to if I'm trying to maximize profit or whatever it happens to be? Okay, in the land of machine learning, this goes under the name of feature selection or feature identification. The word features is used a lot. This is kind of the generic term referring to whatever variables you're measuring, right? In the flowers, it was these 4 things: sepal, lengths and widths, petal lengths and widths. As we'll see in a second, it's a collection of 11 chemical measurements. But yeah, you basically want to find a small subset of your variables which do well in predicting, okay? Maybe not just one, but maybe it's a combination of 2 out of my 11 or 3 of my 11, okay? So for this wine constraint, where this wine data set, you're not going to find this constraint listed in the corresponding repository. I can, in fact, pull it up here. Right, they don't mention anything about like find which of these 11 or so measurements are going to do well in predicting quality or the type of wine, but for the sake of what we're doing here, I'm going to do that. Okay, I'm going to introduce a couple data visualization tools aside from just what I've done so far. In particular, principal component analysis, or PCA, you might be familiar with already, or might be familiar with the acronym at the very least. And then, yeah, the idea of feature selection. Okay, so let's open up a new notebook. So same incantations at the top. Pie plot. What else do we want to do? And use our utility file again. Behind the hood, I am actually using pandas, but I don't really need to use it here. But just to highlight that we are using it, I'm going to import it anyway. Utils.load. I think I called this load wine. Okay, so it's a little different from last time, just by my choice. I'm saving it in a variable called df. Machine learning, or sorry, data science is filled with all sorts of conventions. One of them happens to be what you name your variables. When something's named df, chances are it's probably what's called a data frame. Okay, so if you've worked with R, this might look familiar to you. What this is basically a fancy Excel table, basically. Okay, formatted nicely. Data frames have an enormous number of tools associated with them. When I was showing that Seaborn pair plot thing, it relied on the data actually being in a data frame. Okay, so you wouldn't be able to have quite the same picture just using the data itself. Kind of the key feature, one of the key features is that these data frames keep track of the plain text labels of each of your variables, right? So this isn't just variable 0, variable 1 in the second column, variable 2 in the third column, and so on. It actually remembers, oh, for the 0th column is fixed acidity, right? The 12th column happens to be the quality of the wine, just a score from 0 to 10, and so on. Okay, so this data frame happens to store both the numerical values, which we're going to use to predict the quality of the wine or the type of the wine, as well as the things we're trying to predict. Okay, and you can separate things out. So working with data frames is a class in and of itself. This is also something I don't have any formal training in. So if any of you do have training in working with data frames, then you're probably going to smirk or scoff at what I'm about to do, right? But when I'm confronted with the data frame, probably the first thing I do is convert it into a NumPy array and just work with that. So that's what I'm going to do for the moment, anyway. I'll highlight maybe one or two ways to do the same thing. So the data portion of this is going to be the first 11 columns. Okay, and all of the rows. Okay, so by the way, there's something like 6,500 rows, meaning 6,500 different wines went to this data. They're just labeled red or white. The type of wine isn't really mentioned, but the quality is judged. So someone had to drink all 6,500 of these wines at some point. Okay, so the sequence of incantations here to get the data portion out of this is df. This iloc just refers to the fact that I'm referencing by numbers rather than letter by words. Okay, so I'm saying give me up to the 11th, or really give me the first 11 columns. And then values just refers to the fact that I want a NumPy array out of this. Okay, so indeed, I get something that's a lot simpler when I do these three things. And then for the moment, let me just focus on a binary task. So to show you the different aspect of data frames, this is where the magic comes in and why people in R love R, right? Everything in R, I think, is more or less data frames. You can refer to columns by name. And so you don't have to play this mental gymnastics of, oh, what is variable 13? Oh, it happens to be the wine type, right? You can just say, give me the type, right? Or, give me the pH, I think was one of the other measurements, right? So it can be very nice, okay? In this case, the labels, pretty similar to last time, right, are strings, meaning words, red or white. Okay, and we can play the same type of game. How do I want to do this? I'm really tempted to do the same thing. So what I'm going to do is build a similar type of dictionary that's going to help me scatter plot this. Okay, I'm going to say maybe slightly different words, the exact same thing, just because I know that there's only two types of wines and they're easier to spell. Okay, what I'm saying is, of the wines in either red or white, find where in this list of labels I'm one of those things. And then I can do something like pyplot.scatter data of, So I will once again take my dictionary, take the type of wine, the indices, where that wine shows up, and scatter the data in those coordinates, just to give an idea. Okay. And this time, the labels are something like red or white, red wine or white wine. So naturally, right, red wines are blue and white wines are orange. You can play with the colors as you wish. I'll show you my prepared notebook near the end. Okay. But this time there are 11 variables to begin with, right? If I were to do data.shape, right, this tells me, yes, I have 6,500 wines, 11 variables. When it gets to that point, trying to look at pairs of variables to see what does really well in separating data isn't really a good idea anymore, right? For any in the know, 11 choose 2 is something like 55. I mean, it's doable, but really something you shouldn't do manually, okay? Maybe the most you could do is something like do a histogram per variable, which yeah, let's do it, right? So as some kind of approach for visualizing this stuff, just per variable to get a sense of how things play out. I'm going to use some more advanced tools in Pipeline. Okay, so what I'm going to do is, instead of using what you'll often see is just pyplot.scatter, pyplot.hist, I'm going to make a container for a bunch of plots all together. In particular, I want to make something that is 11 rows long and 1 column wide. Okay, because I want to make a histogram for every single variable that I have. I don't want to bother with the whole pair plot thing. And then for reasons, which will become pretty obvious pretty quickly, I'm going to specify what my figure size is going to be. Let's start with this, maybe 22. Okay, so the commands look mostly the same. Okay, what I need to do is keep track of a few extra things. I want to make 1 histogram per plot. Okay, and I want to look at each chemical property in turn. So I'm saying, really what I'm saying is, for each type of wine, and and a given chemical, make histograms. So I really need to make 2 loops. Okay, so you do need to respect indentation when you're working with Python. I no longer need this j equals j+1 thing, right? I need to loop over for each chemical property. Make a histogram the corresponding plot for each type of line. Okay, let's see what we get out of this. Something bad, obviously. I think it's because I forgot my formatting. Okay, so this thing is running, which you can tell by the star. It takes a little bit longer because it's making, what, 22 histograms, something like that. Well, okay, while we're waiting, okay, let me talk a little bit about what we're gonna work with in a second. Okay, I would still like to linear models, okay. If you are in the realm that you really need an explainable model to give to a boss, or an explainable model for the sake of science, and you have too many to work with, linear models are the way to go. There's this common joke that you pitch that you're doing AI, machine learning, to your boss, when in reality you're going to do linear models over and over again because that's the only thing that works. It's kind of what holds true here still. Okay, so there are many names for various approaches to doing this. Okay, so terms you'll often hear are things like lasso. This is one approach that's popular in statistics land. Another name that you'll hear is elastic net. Another name you'll hear is, I don't want to say rich regression. I don't think they do what I'm asking for. Okay, so these are all fall under the hood of what's called a sparse linear model. Okay, something our own research group here at Colorado State is a particular fan of is sparse support vector machines. Okay, really the difference between these is in the details of the implementation, but they all rely on an underlying mathematical tool called L1 regularization. Okay. And in practice, I haven't really seen a huge case in what I've done for whether one is strictly superior to another, honestly, or whether the results of one are vastly different than another. Okay. All these are approaches to taking in all of your data and all the variables and building a linear model, meaning, let me just jump to the iris really quickly since this is taking forever. Okay. right? When I was only looking at 2 variables, I just had an equation like this for my line. Again, ignore that I screwed it up, right? You had coefficients here. Well, what happens if one of these coefficients happens to be 0? Okay, so if I have a coefficient at 0 or extremely close to 0, what's going to happen is I can just neglect this altogether. So if this represented pedal width, for instance, if there's a 0 here, what this lasso or what this elastic net model or sparse support vector machine model is telling me is that I can classify my various types of irises while being able to disregard that particular measurement. Okay? So that allows you to just ignore that altogether. And that's a very powerful idea, especially when you have more and more variables to keep track of. Like I said, hundreds, or in my own research, it's tens of thousands when you're working with gene expression data. Right? Like if someone's going to build a microarray to measure specific types of genes, they can work with like 10 genes at most. They can't work with tens of thousands. So anyway, this is still running, okay, which is concerning. If anyone got theirs to succeed, feel free to chime in, right? But this can sometimes happen. Okay, so what I'm going to do for the moment is fall back to one that I have prepared. I did many of the same things here. Okay, I'm going to be needing a decomposition in a minute, but I did start with load iris. I built the same equivalence class thing that I was alluding to. And then I started by, okay, wait, I'm sorry. These are flowers, wine, good. Okay, a lot of comments to myself. Equivalence class. I, in fact, made up a couple of colors to use throughout rather than the default colors. I just chose a red wine color and a white wine color for the fun of it. Extra little doodads you don't need to bother with while you're still learning. But anyway, let's jump ahead to this. So this is the result of what I was trying to do. Okay, so all these white wine colored histograms, that's to say everything from the white wine set is a histogram in white wine color, and similarly for the red. I've added a bit of transparency to make things clear to see. Okay, the commands for this are just above. Okay, you don't necessarily need this tight layout thing, but it is just a souped up version of what I was trying to do. Loop over attributes of the wines, loop over type of wine, and make a histogram with some extra arguments. Okay, and so if you look at variables one at a time, you'll notice that, well, some do decently, right? Meaning if you stare at the 2 histograms and ask, are they well separated? And maybe the interpretation of like a null hypothesis and alternate hypothesis kind of perspective, where you're looking for a difference of means and variances and all that junk. Okay, things like free sulfur dioxide as a chemical property doesn't really seem to distinguish white and red wines, whereas something like total sulfur dioxide seems to do pretty well. Yeah, density doesn't, pH doesn't really seem to do well. Sulfates, alcohol content, I assume that's what this is. I don't know if it's just the ABV, alcohol by volume, but in any case, apparently there's no difference between white and red wine. That's something I didn't know. Okay, so when you're first doing feature selection, okay, if you have like a handful that you can still stare at things one by one like this, you can kind of play a game of stacking up individual variables, which seem to, at least by themselves, do decently in separating out the 2 things you're caring about. So maybe I would say take volatile acidity, and let me take chlorides, that's another decent one. Let me take total sulfur dioxide, and maybe sulfates. It's not amazing, but there's a little bit of separation there, okay? If I were to just focus on these 4 variables, that would be one approach to doing feature selection. Right? I say univariately, meaning look at one variable at a time, ask how well it's separated, and then if I believe that I can combine these after the fact to make a more powerful model, then so be it. Okay, so that's what I did here. I picked 4 of them. I only looked at those 4 columns, so this new array called data sub is something that's only has 4 columns. And what I can see is that I can do better in separating out the red wines from the white wines as judged by principal component analysis. Okay. I'm going to go a little bit fast and just allude to some of the things that I'm doing here, but feel free to ask me
Will you be
questions.
sharing some of these finished notebooks?
Yeah, I'm happy to.
Yeah, that'd be great. Thank you.
Of course. And then I wasn't going to do this live. I wasn't planning to, but I went overboard. Something that you'll find is you spend a lot of your time doing things that are not necessarily useful. And one of them is, well, visualization can be useful, but it can be a huge time sink. So I spent a lot of time having fun with these, showing that, yes, indeed, you can separate out red and white wines here. To highlight Seaborn once again as a package, this 20 or 30 lines that I was doing up above can be done in 2 lines with Seaborn. So it can be very useful if you just want a very quick visualization. Meaning here's my red wines in distribution and principal component land, just mapped to 2 dimensions. Here's my white wines. So yes, they can be separated. Cool. There's a lot of stuff here. I have about 8 minutes left, okay? So what I'm gonna do for the moment is just opt to move forward and just allude to some of the challenges of working with real data. I don't know how many of you were lured here by the prospect of working with this COVID data. So I apologize if that was really what you're here for, but I'll do a little bit of it, okay? I don't know if there are any last questions with this Swine Data Set. But yeah, like I said, I'm happy to share these notebooks. Yeah. Okay, so let me just pull up these really quick. This preprint data set, okay, so this is going to be pretty interesting to see what people get out of this. I actually discovered this through a Kaggle competition. I don't actually do anything with Kaggle, but I, at some point in the distant past, subscribed to their mailing list and made an account. And it can be interesting just getting the emails and seeing what kinds of competitions are made available. For those that are not in the know, this is a website where it basically works like a bounty board. So oftentimes company put up a challenge of do a classification task for us. It's not the iris data set, obviously it's things they care about, but do things like classification or regression, like make predictions that are actually useful for companies. And the top prize might be like $10,000 or $100,000. Depends on who's paying and how hard the problem is, right? But in particular, there's one relating to analyzing preprints on the bioarchive, right? This preprint server for research papers related to coronaviruses. Like, so I don't know the details of how they pulled them up, but my rough understanding is they basically search for anything that involved the word coronavirus or SARS-CoV-2, that's the virus, or COVID-19, right, the disease. You know, some simple search like this, and dumped it in a quasi-clean format for people to analyze, right? And they have a list of detailed challenges, questions they want answered, but it boils down to basically learning something, right? There's thousands of papers out there already. And they might say wildly different things, right? We get a sense of what we actually know. That's the question, okay? So even just stating that, it's maybe immediately obvious this is no longer as simple as, you know, here's my labels and here's my data, let's do classification, right? You have to explore the data. So maybe that's all I'm gonna be able to do today, basically. I'm a little bit happy, honestly, because I can't do much more than that. That's not really in my skill set. Like I said, I don't do much natural language processing, but even just a sense of how many papers are directly relevant to what we're doing, or what we're trying to do with, you know, analyzing or learn something about COVID. Where do they come from, right? Any of these questions I think are useful as a starting point. Okay. So kind of coming full circle, okay? When I first, here's my datasets folder, by the way. Here's the main folder. If you go into datasets, I put a script in utils for loading this file, assuming the same folder structure, meaning there's a bioarchive, meta-archive folder. If you unzip this thing, okay, you're going to get a bunch of files that look like this. Now, what is this? I don't know. It's arbitrary blob of numbers and letters, and they all end in .json. Okay. If you're in the know, right, this is a particular type of data format. If you weren't in the know, you could apply my same approach in the beginning of saying, I have no idea, let me just right click and say, open it with my text editor. Okay, so if you do that, well, it looks like this is nicely structured in some sense, right? It looks like there's tabs. I can read some things here. Okay, and I'll allude to the details of what this is exactly in a second. There's things like paper ID. I don't know what this is. It's just a number assigned to this paper. Metadata, you'll notice here's someone's name, Salman Butt from Georgia, right? They list institutions here. I don't say what lab it is in this case, right? An abstract, okay. The text of the abstract seems to be infectious bronchitis causes significant economic losses, blah, blah, blah. And you'll notice there's no mention of COVID in the first sentence. So, well, you know, maybe coronaviruses come up eventually, right? But, you know, who knows, right? They're all mentioning infectious bronchitis. It's not immediately clear if this first paper is going to be useful or not. Something we'll have to develop some tools to analyze. Okay, and so if you scroll down, you'll notice more text. This text was in the abstract. There's body text, right? So this seems like some kind of data format where they've broken things down into smaller pieces and kind of exposed who's writing this paper, where they're from, and the body of the text, the abstracts, back matter maybe. I believe they also, maybe they have text of the tables separately as well. I'm not sure if they include citations, but maybe not. So anyway, right, when you're doing your first data exploration, it can't hurt to do this. It seems, in my mind, it's promising. This isn't going to be a huge pain to load. But if you see a particular data format, meaning this suffix JSON, you should not try to reinvent the wheel. So I could, with enough time and effort, write some script to pull out the title, this manually from every single file that looks like this. And then they're all going to look like this, basically. Okay, but I really shouldn't reinvent the wheel for two reasons. Saving my own time is one, and then for another reason, if anyone else is using your data, chances are they're trained to understand some conventions. One of these is common file formats. So one of these is JSON, or you'll hear it called JSON, or just JSON in the field. Okay, so once again, my utils file basically boils down to using a package to load JSON files. It takes a few seconds to load, so if you were to type these out and then load bioarchive in this next line, it's not immediate, right? Because you are reading 1,000 papers, basically. I wrote out a small script to print out some progress, so I'm not just sitting on my hands nervously. Okay, so yeah, so we've basically run out of time, right? But this is indeed basically the same thing that we saw in this text file. If I were to ask what's my 0th preprint, it happens to be a dictionary. I can tell by these curly braces, and it has many of the same things that I can kind of pull out that I could inspect by eye. So if I were to ask, if this is my paper, tell me what the metadata is. Right, that was one piece that I saw. Okay, well, there's even a lot of information here. Okay, so tell me of the metadata, tell me the title. Okay, so if I were to ask a very simple question like, give me the title for every single paper out there, I can pretty quickly adapt this into a simple loop and try to evaluate something like, okay, it's done. My titles is an enormous list of things. I could ask something like, does SARS coronavirus 2 show up in the title at all, right? So So this first piece basically says, is this string showing up in the title at all anywhere? Okay, these are all instantaneous, fortunately. This hits is going to be true or false. Okay, so it seems like there's some. Well, okay, so it seems, at least in the titles, right, neglecting the body, neglecting anything else, of these 1,053, only 109 have SARS coronavirus 2 in the title. Okay. And you can say, well, this was too limited. Okay, maybe I should look for more broadly. What if it's coronavirus? What if I have to worry about things like capitalization or things like that? This is just the start of how you begin to analyze this type of data. Okay, there's no clean answers. And then you have to do a lot of just print out these complex data sets and narrow down to what you really care about and formulate questions along the way. Okay, so even though I found 109 papers on SARS coronavirus 2, right? I don't know why that screwed up, but oh, I know why. Right, of these 109, right, you can ask further questions or do natural language processing or any number of things, but it's not easy. Okay, so anyway, this 11:32. So I'll just stop talking for the moment. I'm happy to take any final questions. Otherwise, you're welcome to email me. Yeah, thanks.
Well, thanks so much, Manuch. I just want to really thank you a lot for the great tutorial and just repeat some information for people who did not connect at the very beginning. So we're going to post this on the PAC tutorials webpage, which is colorado.edu/PAC/tutorials. And yes, Manuch, you mentioned you're going to post the complete notebooks. Maybe on the same GitHub page, the same repo that you had the material on.
Yeah.
So that's already, that link is already being sent via the email announcement, so people know how to retrieve your GitHub repo. I really want to thank you so much, and we'll be happy to take any questions even about this series of tutorials, or unless you have questions for Manuch.
Be sure to unmute yourself, by the way. So the one thing I'll point out is this PAC tutorials website. The preview is here. The GitHub repository has its own link at the bottom. So yeah, check back here in like 10 minutes. I'll upload it after we've closed out the Zoom call.
Yes, thank you so much for showing that page. So any questions for Manuch or for us organizers? Otherwise, I think we can just close the meeting, and I really thank you so much, Manuch.
Yeah, happy to.
Okay, well.